evening. For this programme, we're going to talk about robotic telescopes. But first, a couple of news notes. I'm very sad to report the death of a very old friend of mine, Professor Fred Whipple, the American astronomer, probably our greatest authority on comets, and the man who put forward the dirty snowball model that turned out to be right. And now, on a happier note, the planet Mercury. Now, Mercury is never very easy to see, either low in the east before dawn or low in the west after sunset. And this month is going to be in the east after September the 8th, and you'll see it quite well with the naked eye. But don't sweep the binoculars unless the sun is actually below the horizon. But Mercury's there, and on September the 10th it'll be quite close to the bright star Regulus. And the Americans are sending a probe there. They launched Messenger to Mercury, only the second Mercury probe, and when it gets there, it'll tell us much more about this strange little world that we know now. But I don't think I'll be on the sky tonight then, because it won't enter orbit round Mercury until the year 2011. Some years ago, Liverpool John Moores University had the idea of setting up automatic, robotic telescopes in various parts of the world to make quick observations of things like supernovae and get early accounts of them. And that's not been done before. Well, I'm proud to say I did have a very large say in the early arrangements, for now the first telescope is operating on La Palma. And so now, over to the Canary Islands and Chris Lintott.
I'm standing 9,000 feet above the surface of the Atlantic Ocean at the peak of the Roc de los Muchachos on La Palma in the Canary Islands, one of the world's best sites for optical astronomy. The skies are almost always clear. You can see we're above the clouds up here. And the atmosphere above me is very, very still, leading to perfect seeing conditions for the large telescopes arrayed across the mountain. We're here to look at the newest of them, the largest robotic telescope anywhere in the world, built in Liverpool.
It occurred to us many years ago that actually we needed a telescope that could react very quickly to things that essentially go bang in the night, some of the most dramatic events in the universe. And at that stage we really didn't have access to anything like that. And so the idea of a robotic telescope like the Liverpool telescope was born.
So how did you go about turning that single idea into the reality we see behind us?
Well, it's been a very long and slightly rocky road, but one of our first thoughts was actually to convert an existing conventional telescope to become an automated robot, essentially. But we soon found that that was a bit like trying to convert a Ford Anglia into a Rolls-Royce, and you end up with a lot more money spent and probably not the same result as starting from scratch. So then the problem became, how do we actually do this? How do we acquire a fully robotic telescope for UK and international astronomy? And we ended up having to design and build this in the UK, and the product of those 15 years of endeavour is now behind us in the form of the Liverpool telescope.
What does it mean to say a telescope's robotic?
It means it's a fully autonomous system. We look on this as being like a space probe but on the ground. The advantages of this are that it's a very efficient system and it can react very quickly to things that change. The advantages also, compared to a space probe, is actually that you can get to it and you can fix things, because things are going to still go wrong with it, obviously, and we need to maintain it.
Its entire mode of operation is revolutionary. Instead of having to travel to observatories and carry out fixed programs of research, astronomers with the Liverpool telescope could schedule their observations in advance and respond rapidly to whatever's happening in the sky.
One thing that makes it move very rapidly and smoothly is the fact it's actually floating on a bed of oil, if you like, a very, very fine bed of oil.
Just a few millimetres.
Well, not even that, microns we're talking about. And that's right in the bed of the telescope here. It's also got the same sort of system on the altitude axis. So we have the azimuth axis down here and the altitude axis up the top. And then we have a third axis of motion, which is the rotator, which has the instruments on it, Cassegrain rotator. So actually the telescope is moving around three axes very smoothly and can do so very rapidly. It's built also so that it can actually be in a fully open enclosure. So it's a telescope that doesn't shake around a lot when the wind blows, because obviously we're out.
Certainly looks sturdy with these large pillars.
Yeah, it's if you think of a telescope a bit like a tuning fork, the more massive that thing is, the lower the frequency it would vibrate at, and the more it would actually react to wind. So what we've got here is a lightweight, very stiff structure which has what's called a very high natural frequency, so that when the wind blows on it, it doesn't react to that wind very, very much. It doesn't shake around so much. So it can actually be in this open enclosure and doesn't affect the image quality that you get by shaking about.
The enclosure is certainly unusual. I don't think I've seen anything like it at a major observatory. What drove you to this design?
Well, there's lots of advantages and one or two things you need to be aware of. Obviously, a disadvantage is the fact that you are now out in the open air. You're open to the elements. I've talked about the fact that it's very resistant to wind shake. But the advantages for astronomy are tremendous. First of all, here we are on one of the world's best sites. So the image quality here is absolutely superb. And part of what degrades that image quality, the major thing, happens to be the very local environment within a dome.
Heat gets trapped, air gets trapped.
Exactly. When you open a slit in a dome, the air rushes out and the image quality suffers. And so you have to wait for that to settle down and so on. So we don't have a dome here. So we're actually sampling very quickly the image quality of the site. And we do have extremely good image quality here. The other advantage is that we don't have to wait for the dome to go round because we don't have a dome. And because the telescope moves very rapidly, you're limited in how rapidly you respond, not by waiting for the dome to go round, but just by how fast the telescope moves. And the telescope does move very rapidly indeed. The other really important part of the telescope is the software, however. We have a layer of software here that takes the place and does rather better than, perhaps unfortunately for us, the human observer. It doesn't get tired. It makes very rational decisions.
Even at 4 o'clock in the morning.
Even at 4 o'clock in the morning, yes, when, with the best will in the world, the best of us are not making necessarily the best decisions about what target to observe next and how to go about it.
The Liverpool Telescope's research covers the whole spectrum of astronomy, from comets to extrasolar planets to active galactic nuclei. But the real advantage of a telescope like this is when you study things that change rapidly. Explosions.
Well, really what we want to do is to get onto the explosions very rapidly, to see the initial rise to the peak brightness and then the decline away. I'm particularly interested in classical novae. Classical novae are in binary star systems where the two stars are so close together that material is being drawn from one onto the surface of the other. And the star from which material is being drawn is a star like the Sun, a bit cooler, so-called main sequence star. The star on which the material is landing is this very dense object called a white dwarf, and every 10,000 to 100,000 years or so, the material on the white dwarf reaches temperatures and densities such that a runaway thermonuclear explosion can occur, and we see a nova in the sky, up to 100,000 times as bright in terms of its intrinsic luminosity as the Sun. And classical novae are important for all sorts of reasons. They produce lots of dust, and some of that dust actually ends up being accumulated back into planets. Very small amount of nova dust actually is involved in that. But we can actually see that dust formation in real time in classical novae. They're also sort of beacons in the sky. If we can understand a little bit more about them and the way their brightness changes, it's been known about for quite a long time that potentially we can use them as things called standard candles. That actually, if we know how intrinsically bright they are, and we know how bright they appear, then we can find out how far away they are. The problem has been really getting enough systematic observations of that brightness change of a classical nova to calibrate effectively that standard candle relationship for them. Now we see only a few classical novae in our galaxy per year, and distances to them are fairly uncertain, so to actually use them to calibrate this relationship is rather difficult. So what we do is we look at other galaxies, and this is one of the other programs of the Liverpool Telescope, is to actually find classical nova explosions in other galaxies millions of light years away.
One of the problems is that they're still, although explosions, still relatively faint, which brings us on to supernovae, which are what they sound like.
Absolutely. A supernova explosion, unlike a classical nova where the system can sort of recover and you can get another outburst, a supernova explosion is the catastrophic death of a star. One type of supernova originates in a star at least 8 times as massive as the Sun. And when it comes to the end of its life, it's trying to burn iron in its core. When it tries to do that, that actually takes in energy rather than giving it out. It can't then support itself against collapse. The whole thing collapses. And for reasons that we don't absolutely fully understand, this bounces and you get an explosion rather than an implosion. And we see a supernova in the sky, and the remnant of that could be either a neutron star or a black hole.
And most of the material from the envelope of the star, the atmosphere of the star, shoots outwards into interstellar space.
Absolutely.
We see that with the most recent nearby supernova, 1987A.
Yes, in fact 1987A is still evolving before our very eyes, and we're learning an awful lot about how supernova explosions work and the interaction with the interstellar medium from the studies of 1987A.
Now, a single supernova can outshine in the sky the entire galaxy that it's part of.
Yes.
In fact, that's quite common.
Yes.
But even supernovae pale by comparison with our final class of explosion, gamma-ray bursters. First of all, what's a gamma-ray?
Okay, well a gamma ray is very, very short wavelength radiation, and thankfully it doesn't penetrate the atmosphere. So if it did, life wouldn't exist on the Earth. But that means to actually study things at gamma ray wavelengths, we have to put satellites into space. Now, the United States in the late 1960s had a class of satellites which are military satellites called the Vela satellites. And they were actually looking for violations of the test ban treaties in space. So they were looking for the gamma rays that are given off by nuclear explosions that are man-made, artificial explosions. Thankfully they didn't find any of those, but they very rapidly found gamma ray bursts or gamma rays coming from sources randomly spread across the sky, and they were finding many, many of these. It's about 30 years actually after the discovery in 1967 of gamma ray bursts. They followed up optically for the first time a gamma ray burst that had occurred about a day before. By this time in 1997 there was flying a satellite called Beppo-SAX that could pinpoint within that period of time, hours to days, more precisely enough where the gamma ray burst had occurred on the sky for an optical telescope to stand any chance at all of pointing in the right direction. And they found what's called an optical counterpart of this gamma ray burst. Subsequently, they were able to take a spectrum of the fuzzy blob in which it sat, and this turned out to be a galaxy, and that galaxy had a significant redshift, which meant that it was at so-called cosmological distances. And we now know of certainly more than 30 gamma ray bursts with an optical counterpart, and they're all at enormous distances.
And those determinations of distance have helped us try and understand what are gamma ray bursts.
Well, yeah. The ones that we've actually found the distances to are all one type of gamma ray burst. They're actually short bursts, which don't last very long at all, and long bursts, which don't last very long either. But the long bursts last long enough for us to be able to point telescopes to the regions of space where the gamma ray burst has been seen, and then follow these things up optically. In fact, one went off in January 1999, I think it was the 23rd of January 1999, which was so bright that you could have seen it if you'd known where to look with a pair of binoculars from your back garden, and yet this is something that's billions of light years away. So you've got an enormous amount of energy being given out. So there's something really, really exotic going on. The favoured theory at the moment for the long bursts, where we know a little bit more, is that they are hypernovae. In other words, stars even more massive than the stars that are giving rise to the normal supernovae, perhaps 30 or more times the mass of the Sun in this case, come to the end of their lives and explode even more titanically, if you like. The short bursts, the favoured theory at the moment is that these are due to the coalescence of these very exotic objects, black holes and neutron stars, which come together and then give out a huge amount of energy. But the real key to understanding these things is to get onto the bursts very, very rapidly from the ground with optical telescopes and see what's going on in the first few minutes.
Next month sees the launch of NASA's SWIFT satellite, providing the best early warning system we've ever had for these gamma ray bursts. Several of the instruments on board were built by British institutions, the X-ray camera from Leicester, for example, and the optical device from Mullard Space Science Laboratories. Once Swift detects a gamma ray burst, it will send a signal down to Earth, and observatories like Liverpool will be able to respond rapidly to these signals and capture the first few moments of these dramatic explosions.
The Liverpool telescope should be able to follow up observations from Swift at the rate of about one a week. Now the Liverpool telescope, because it is so rapidly moving and can respond automatically without human intervention, these are signals that come from the satellite through the internet essentially straight into the scheduler of the telescope, interrupt absolutely everything. It can then move and get onto a gamma ray burst source within 1 minute. So I think there's going to be a revolution in our understanding of what gamma ray bursts are all about over the next couple of years.
It's night time here on the Palma, and the telescope's already well into its programme of observations for the evening. I have to say it's one of the darkest skies I've ever seen. The Milky Way is obvious as soon as you step out the door, and the centre of the galaxy is much higher up in the sky than we ever see it from Britain, and the detail is quite amazing. Meanwhile, Mike's been looking at some of the most recent novae and supernovae the telescope's been studying.
Well, the last few nights have been really exciting with the telescope, particularly in the area of novae and supernovae. I was saying earlier on that we discover probably only 2 or 3 novae in our own galaxy every year, but a bit like London buses, we've got 2 that have come along in very short order, both of them in the constellation of Scorpio, and one of them was discovered only last week. And the image on the left-hand side here shows that nova in the constellation of Scorpio, which is actually very, very bright and was discovered, as most of these things are, by amateur astronomers. And then on the right-hand side here is an image of a galaxy, a much more distant object, and you can probably see this small stellar image. Looks like just a normal star, but it's on the outer edge of this galaxy, and in fact this is a supernova. And this is a really exciting discovery that was made by an amateur astronomer in the UK called Tom Bowles. Only a couple of nights ago we were alerted to this, and we observed it for him because he couldn't really absolutely confirm this was a supernova. We needed the capabilities of the Liverpool telescope to go that much deeper and confirm that this is, yes, a star on the outer edges of this spiral galaxy that wasn't there before, and as you can see it's actually outshining most of the stars in its parent galaxy.
Although it's primarily a research telescope, amateurs and schools have the opportunity to use the Liverpool telescope themselves. 5% of the observing time is set aside for these programmes, and it's a fantastic opportunity. The Liverpool telescope is now in full operation, and there are another 4 robotic telescopes either in situ or under construction.
Well, we have a plan to have a network of robotic telescopes around the globe, able to act as one unified telescope, as it were, to be able to look at anything on the sky, any time of the night or day, and to continue to observe it by passing observations from one telescope to the next, as the sun comes up at one place and it's dark at another. And there's a whole range of things that a network like that could do. And our sort of prototype network, RoboNet 1, as we've grandly christened it, has already begun operations this month.
And so the first telescope is now in operation. Chris and Mike, thank you very much. Something new now, the discovery of extrastellar planets about the size of Neptune, going round other stars. Does it lead on to the discovery of other Earths? Well, it could do. And our programme next month is going to be entirely about that. So until then, good night.